defined functions, you've got multiple parts. Sometimes there's 3 parts, sometimes there's 2. Technically, there could be an infinite number of parts out of that, but the theory works no matter how many parts you have. What you've got is you've got a function, like 3 separate functions for certain parts of the domain. Okay, so we've got 3x plus 2, but that only works when x is less than or equal to -2. Okay, so that's the domain for that particular function. And then f of x equals 6 when x is between -2 and 4. That's what that's telling us there for the domain for that part. And then it's given us that f of x is -2x when x is greater than 4. So we've got 3 different parts of graphs here that are going to end up on the same coordinate plane. So what we want to do here is start out with just the first part, and what I like to find are the important points. And the important points with piecewise defined functions occur where there's an interesting place in the domain. So with that first one, the interesting place in the domain is at -2. Okay, so when x is -2, what's the y value that goes with that? So to find that, we're going to take that -2 and plug it in for x in that function. So 3 times -2 would be -6 plus 2 would be -4. Okay, so that's an important point for that particular part of the graph. Okay, so on the coordinate plane, we're going to go graph that particular part of the function. All right, bless you. Y-axis, I'll do it by hand, and then I'll show you how your graphing calculator can handle this as well. So x-axis, and so at the point -2, -4, -2, -4, and I'm going to put an open circle there because that is a less than symbol. It's not equal to. Okay, so that means that's an open circle on the graph. So it's a hole on the graph. And then I know that all the other x's for that particular part of the function are less than -2. So I know that that's going to go toward the left on my graph. Happen to know that that's a linear function with a slope of 3. So I could follow that pattern, go down 3, left 1, down 3, left 1, and I get that graph. Another way of getting that part of the picture would be plug in some x values that fit into this inequality. You know, I could plug in -3 and -4 and -5 and get that side of the graph and what's going on there. You could do that either way. I'm going to use the slope form there because I know it's a linear equation. It's quicker. So there's that piece of the graph. Okay, and then from there we move on to the second part, and it says that y is equal to -6 or to +6 when x is -2 all the way up to +4, including both of those. Okay, so the important points for part 2 or part B there, whatever you want to call it, are happening at -2 and +4. So what we need to know are what's the y value that goes with -2 for that part of the function. So if this says y equals 6, that means y equals 6 no matter what x is. Okay, so that ordered pair is going to be -2, 6. And the other ordered pair, the other important point, is also 6 for the y value. Okay, if there had been an x in that part, we would have plugged it in and worked it out. Simple part there. Okay, now those 2 points are included. So when I plot them on the graph, 2, 4, 6, they're going to be filled in dots. And I know that y equals a number is a linear equation, and it's horizontal because it's y equals a number. Just general knowledge about functions. So that's the graph of part 2. Okay. Then part 3, where's the important point going to happen there? Well, that's the function. At 4 on the x-axis. So the y value we need to find using negative 2x. So 4 plugged in there, negative 2 times 4 would be negative 8. So that important point is at 4, negative 8. Is that an open circle or a filled-in dot at that point? Open, because it doesn't have an equal to mark. So we're going to put that point at 4, negative 8. 8. And we know that's what kind of line or what kind of graph. I kind of gave it away. It's a linear equation because it's just got plain x in it. And it's got a slope of negative 2. So I can take from that point and count down to right 1 and get several points on that if I wanted to. I can get as many as I want to. Or I could take the x values that fit in this inequality up here. Pick x values that are greater than 4 and plug them in and get some points. Okay, I just need some points to get the picture of what's going on. All right, so those points are the ones that I've marked there. So there would be the graph of that piecewise defined function. It's not pretty. It's pieces, 3 separate pieces in that case. But what we're one of our jobs here is to find the domain of that function, okay? And then we're going to find the range. And then we're going to find the intercepts. And then we're going to talk about this thing called continuity, which is the easiest part. Okay. Domain can really be found without even having the graph. The domain is given to you over here on the right. It's all these inequality things, okay? So it's telling us that all x's that are less than negative 2 are part of the domain. That's what the first part is telling us, is that x is less than negative 2, so it goes all the way up to negative 2. And then what we've got to check and see is negative 2 picked up in the next inequality? So negative 2 is not used in this one. Is it used in this one? Yeah, it's got an equal to mark on it, so that means negative 2 is picked up. So far we're going all the way from negative infinity. We're including negative 2, and then this tells us to keep going until we get to 4. And then at 4, is 4 included right here? Yeah, it's got an equal to mark, so it's included. So far we're all the way from negative infinity up to 4, including 4. 4 is included on this one, but is it included on this one? But it is included, right? Okay, so we're going to keep trucking from 4 to x is greater than 4. So that's going to get us all the way up to what? Positive infinity. So our domain for this one is from negative infinity to positive infinity. Because anywhere that they jumped and went to the next function, it picked it up. Okay? There wasn't an empty spot in the domain. Now, the range is a little more difficult to find without the graph. If you've got the graph, range is much easier to find. So my suggestion is if they ask for the range, get the graph and then get the range. Okay. So remember, with domain, you're reading left to right. With range, you want to read from bottom to top. Okay. So we look at the bottom of our graph. What are both of those blue and green arrows doing? Keep going down. Yeah, they're decreasing toward what? Negative infinity. So we're going from negative infinity, and then this one stops at this place. What's that y value right there? Is negative 8 as a y value used by the blue one? I go over here. Yeah, it's one of the points. It's not a hole there, right? So that means we're now riding this one. We're on this track. We're going up through here, and then what's that y value? Negative 4, right? 1, 2, 3, 4. Negative 4. And is it included? No. And is there anywhere parallel to it that's using it? No. So we're going from negative infinity up to negative 4. We're not including negative 4. And then we got to go keep reading from bottom to top. What's the next y value that gets used? 6. Is there anything higher than 6 that gets used? No. Is 6 included? Yes. So we put brackets around it. So from negative infinity up to -4, that gets us the blue and the green one. And then we jump from there to 6. And that's, we're on the red piece, we're on 6 the whole time. And then it doesn't go anywhere. It doesn't go up from there toward infinity because there's no arrow pointing up. Okay. Yes, sir.
So on the test, a lot of the time when it was asking for a name, it say something like all real numbers.
That's the same thing as negative infinity to positive. Those are the same thing. All real numbers and that are the exact same thing. Good question. Okay. All right. Intercepts. What kind of intercepts can we have? X and Y. Okay. Does this one have either of those? It has a Y intercept. Where at? 0, 6. So the ordered pair is 0, 6 for that intercept. Okay. And then the last thing we want to talk about is continuity. Continuity is whether the graph is continuous or not. If something is continuous, it means it just continues without stopping. Okay. And one of the best ways and the easiest way for me to explain this to you is if it's continuous, then I should be able to start on the leftmost point on the graph and trace it with my pencil. And if it's continuous, I'll never have to pick up my pencil to get to the next piece. That's maybe the best way I can explain it to you. So if I'm tracing this from the leftmost point, there's the blue piece, and I get here, and then I've got to jump up to the red piece to get to the next place. So I can't trace this without picking my pencil up. So this would be what we call discontinuous. Because we could not trace it without picking up our pencil. Continuous graphs, you never have a place to jump over, even if they, if you had 2 points that, one of them ended here with an open circle, and then the next piece, did this. That open circle creates this discontinuous graph because there's a place you got to jump over out of that. If that's a filled in dot, then that becomes continuous. That's the difference in those two. Okay. So empty circle, that's discontinuous. Filled in circle, oh, that's continuous now. Even though the graph looks almost exactly the same, that hole is the difference. All right. Now let's look on the graphing calculator and how we can get it to mimic what we've done here. Okay. Pretty easy to do. You just got to remember you're going to use parentheses and some inequality symbols along the way. So, and where to get those is what you need to know. So, hitting y equals, and I was doing this today in my high school class, so I'm going to clear this stuff out and start from scratch, even though that's the same problem. All right. With this, you're going to have 3 separate graphs. You're going to have y1 is going to be part A, y2 is part B, y3 is part C, okay? And what you want to do there is put each function in parentheses. So I'm going to start with part A, and I'm going to put in parentheses 3x, parentheses, which parentheses is right above the 8 and 9. So 3x plus 2, close the parentheses. And then I'm going to put a division symbol. And then I'm going to open up another set of parentheses. And this is where I put my inequality in. So I'm going to tell it that it needs to be when x is less than -2. So to get the less than symbol, you're going to hit second math. There's one way to get it. There's other ways, but second math is the most, to me, the easiest way to remember it. Second math, and then we want less than, so that's choice 5. We get a less than symbol. And then we use -2 because that's what's in our inequality. And then close those parentheses. I'm going to hit graph and show you how that just does that first part. There's that blue piece from my graph over here. That's that same blue piece. All right. Now I need to go to y equals, and in y2, I'm going to put in the y equals 6. So in parentheses, I'm putting a 6. And then divided by Here, the compound inequality is a little bit more difficult to do. What you've got to do is do it in two separate pieces, but put the word and between them. I'll show you how to do that. It's pretty simple from there. You can really just take it and say -2, and then we need a less than or equal to symbol. So second math less than or equal to is choice 6, x. And now we need the and, so we can do the other end of this. So second math, and then go over to logic. And we have ands, ors, and XORs and nots, but and is the one we need. So it's a compound inequality with an and. And then we use the other end of that, x is less than or equal to 4. X, second math, less than or equal to 4. So 6, 4 there. Close the parentheses. So we should be seeing the blue piece and the red piece from my graph that I drew by hand. So I hit graph, and we see that red piece right there at the top. So beautifully. If you got the black and white version, you'll just have two black versions there. Let's get the last piece. Go to Y3, and in parentheses, we're putting in -2x. -2x. Close the parentheses. Divided by, and then put the inequality in, x is greater than 4. X, second math, greater than, choice 3, number 4, close the parentheses, and hit graph. We see our picture pretty much as I drew it by hand. You could zoom out, zoom in if you needed to, whatever from there. Okay. We'll look at it on the calculator as we go through another example. Just get some more practice doing that. Takes a little practice, but that can be helpful, especially in finding the range instead of hand drawing everything. That can be difficult. The only thing you lose on that is you don't specifically see the open circles and the filled in circles at the end points, those important points. And you've got to know whether they're open or filled in. It's important when you're writing your range or your domain as far as that goes. Okay, so you got to know that part without just relying on the calculator to give it to you. What error is it saying?
It's saying on the second one, the Y2, on the less than or equals to part.
Did you put and between them?
Yeah.
You got 83. I don't know. I'll get rid of the X. Right there between the and that's one of the errors. Anybody else got an error that they want to address?
I get an error, but I can barely see it. Okay, trying to figure out.
So get your picture zoom 6. We'll get you back to the normal window.
Oh, okay.
Zoom, guys, if your window if you zoomed out or zoomed in somewhere and you need to get back to the one that is this size, zoom 6 on your calculator will get you back there. That's always the default for that. Okay. It's a 10 by 10 window is what it defaults to. All right, let's look at another one, a little bit higher level function. Example B, g of x is equal, and I'm only going to put two parts in this one, x squared when x is less than 2, and then -3x plus 5 if x is greater than or equal to 2. So again, let's do it by hand and then do it with the calculator as well, so we can just we get some practice with the open circles and the filled in circles and hand drawing some of this stuff, just so I think it gives you a better understanding of what's happening across there. So what's the important point for the first part? The x value would be 2, and the y value would be 4. Okay, is that point included or not? Not, because it doesn't have the equal to mark on it. Make sure you got a little bit of room in both directions here. It doesn't have to be a big one for this one. So at 2, 4, I'm going to put an open circle. What do we know about the graph of x squared? Just general knowledge about x squared. Anybody know anything about it? It's a parabola. Parabola is that U kind of shape. Looks a little bit like that on there. So what's another important point when we're talking about quadratics that could be handy for this one? Like the change in direction point.
Yeah.
That's called the vertex. Okay, that's an important point for this. And where are our x values that work in x squared for this problem based on the inequality beside it? Anything less than 2. Okay, so even if I don't know any of that stuff about x squared, I can still get the picture by just picking some x values that are less than 2 and plugging them in. So if I pick 1 and plug it in, 1 squared is 1, right? So that 1, 1 is a point. If I pick 0, that's less than 2. 0 squared is 0. And if I pick -1, what's -1 squared? +1, right? You multiply it out. And then if you pick -2, what's -2 squared? +4. And if I pick 3, -3, I could go further there. So we kind of see that this shape, what's going on here is kind of this. Not kind of that, it is that. It's a pretty good parabola. You say so myself. We get that idea. So we're getting the idea of what the shape is. And then from there, we go on to the next piece and get its important point, which is where? At 2, plug that in. +1 or -1? -1, because it's -6 plus 5, which would be -1. So we're going to 2, -1. And is it an open or filled in? Filled in, because it's got an equal to mark. And then we know that -3x plus 5 is a lot like some of the other stuff we saw in example A. It's a linear equation. The slope of -3. I could go down 3 and over 1. But remember that I also could just pick x values that are bigger than 2 and plug them in. If I don't know anything about the graph, I can still get the graph by plugging x values in, okay, and get those same points that I've drawn there. And then those that direction. Okay, so we see the graph. From that, we should be able to get the domain. We don't even have to have the graph to get the domain. So what's the domain of this thing? I think positive, all real numbers are -infinity to +infinity. Same thing. Because here, it's going out to the left all the way there. And it just keeps going. And then we get here to 2, and it jumps down, and 2 is used right there. So we don't leave it out, we pick it up. And then it keeps going out toward +infinity here. So there we have from all real numbers or from -infinity to +infinity. The range for this one. Read it bottom to top. So we start with the red one because it's on the bottom. -infinity, obviously, because it's pointing down. And then where does it get to? -1. So at this place right here, there's -1, and it stopped. Is there anywhere to the left or the right of that spot that uses -1? No. So we know it's going to pick up from -1. Is -1 included or excluded? Why? It's included. Why? I got the equal to sign on my domain up here, and that's a filled in dot on my graph. Okay, so bracket on that. What's the next y value that gets used? 0, because we jump up to the blue part, and the lowest one there is 0, and then it goes where? To infinity, because that left side just keeps going up forever. There we have from 0 to infinity. So that's the range out of that. Let's run through graphing that on the calculator real quick, because that's the graph on the calculator can help you find that range if that's all they're asking for. So graphing calculator, I'm going to clear out this stuff. We got x squared divided by, and then we're doing x is less than 2. X, second math, less than is choice 5, 2. And then the second part, parentheses, negative 3x plus 5, close parentheses, division symbol, parentheses, x, second math, is greater than or equal to 2. Greater than or equal to is 4. A little shorter on this one as far as that, getting all that stuff typed in. And then I hit graph. And I should see very similar graph to what I drew out of that. And that can help us get that range out of that and see the only, like I said, the only thing that's happening there is you're not going to see the open circle, filled in circle. You can actually find those using the trace function, because we know things are happening at 2. So if I hit 2 on the blue one, notice that the ordered pair at the bottom, it leaves the y blank because it's open. So we know that that y value is not used. So it's open there. It doesn't draw an open circle there for you. You just have to know, oh, at 2, something's happening. And you check that place, and there's y not being used. And if I swap over to y2 by pressing the down arrow and then try 2 again, notice it gives me the y value that I used there out of that. I don't think it's quite as in your face as the hand-drawn graph is, because the hand-drawn graph, we start with that open circle or filled in circle. And that's the important point. So that's why we start with that. With the graphing calculator, it's kind of, it leaves you hanging on those things, which is not always good for you. Okay. While we're still on this one, let's do intercepts. 0, 0 would be the only intercept we have. It's technically an X and a Y intercept. It doesn't really matter about that. And is this continuous or discontinuous? Discontinuous. Guys, honestly, doesn't get any more complicated than that with a piecewise defined functions. You're just you got to take it piece at a time, get it drawn, figure out what the important points are, because that's where your domain and range is going to do something at, is those important points. They're going to give you that domain on the right-hand side and tell you what's going on. There's really not, a whole lot else going on with that, okay? So it's going to take some practice with some piecewise defined functions. All right, let's go to the next section. Regular paper will be fine on this. We're going to discuss some translation and transformation theory here. My cousin, who's a computer programmer, and he works for a company called File Tracker. If you work with law firms or anything like that, they do work for them, and they're in charge of making sure files for the court system are secure and everything. But he and I were talking over holiday break. They were in visiting, and he was talking about any math class that has the word theory at the end of it was no fun, because he took a lot of math in his undergrad to get his computer science degree. And he said, I found out pretty quick not to take the math classes that said theory. So the sections that say theory are not always the funnest in the world. But I try to make this as simple as possible and give you a concrete idea of what's happening as we go along. So when we're talking about graphing techniques, the idea is that you would be able to take a function and just based on the information that they give you about the transformation or translation that they've done, write the equation of that function. Okay, so we're going to say y equals f of x. So we know that that's true, that y is the same thing as f of x. But we're saying y is the function. And the original function, no matter what kind of function it is, if it's an x function or if it's if it's an x squared function, no matter what kind of function it is, the same things happen to it given a certain situation. All right. So there's a thing called a shift. And in life, there are vertical shifts and there are horizontal shifts. If it's a vertical shift, then what's going to happen is the function is going to get something added to it. We're going to call it k. Okay, k is just a number. Okay? We're adding something to it. If k is positive, what's going to happen to it? It's going to go up. Okay, if k is positive, it's going to go up. K is a plus sign, we're going up, shifting up. If k is negative, guess where we're going? Down. Okay. Example of this would be if, I'm just going to be referencing the graphing calculator a little bit just to give you some ideas of what's going on. If our function was x squared, the original just x squared, here's what the original graph looks like. If I add something to that, like on y2, I type in x squared, and then I say plus 3. That should take that blue graph and shift it where? Up 3 units. It's just going to pick it up and move it up 3 units. So I hit graph, and there's the original. The red one is just taking this blue and going boom, 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 3 times. Up 3 units. So it's a vertical shift. Okay, if I subtract something from it, so instead of adding 3, let's say I went to that and said, okay, what if I just change that to a minus 3? It's going to shift it where? Down 3 units. So take the blue one. There's the original. Here's the minus 3. Just shifts it down 3 units. Doesn't stretch it out or anything like that. It just takes it, picks it up, and moves it down 3 rungs on the ladder. Okay. So if that's all that's happening, a plus or minus a number on the outside, then that is a vertical shift either direction. Plus is up, minus is down. That's very simple idea. Anything that happens on the outside is going to be vertical. Okay, that's going to be key as we go later on. And I'll say that over and over so you'll hear it again. All right. A horizontal shift. That's where something happens on the inside. If it's a plus k on the inside, that k is, again, it's just some arbitrary number that we're adding or subtracting to the x on the inside. That's going to shift it to the left, k number of units. Okay. If it's y equals f of x minus k, so they're subtracting something on the inside, it's going to move it to the right, that number of units. Let's look again at our graph here. Again, we're starting with x squared. If I'm going to add something to the inside, so that'd be x, let's do plus 2, and then it's squared. That's what I'm saying there. That should move it to the left 2 units. So when we graph that, here's the original. There's the one shifted to the left 2 units. Okay, that's what's happening there. Okay, so the idea here is that you would be able to look at an equation or look at a graph and be able to determine its equation without having to graph it and tell what would happen to the graph without having to do that. Okay. So horizontal happens on the inside. Vertical happens on the outside. I said it again. Vertical stretch. I don't know. You guys may be too young. I don't know. You might ever play with silly putty when you're a kid? Did you ever take it and the comics that come in? Before long, this will not be an example I can use because nobody gets a newspaper anymore. But if you had the newspaper, you could take that silly putty and smack it down on that newspaper and smooth it out and pull off a picture of Garfield or Charlie Brown, or whoever you had. And then you could stretch it and make them taller. I could make Garfield skinnier. I could make Charlie Brown's head not so big around, you know, that sort of thing. You could stretch it. A vertical stretch is doing that. So it's like taking that X squared graph and pulling it this way, and it's stretching out and making it skinnier. That's what it looks like it does. Okay, and that's going to happen when you multiply the function by something that's greater than 1. It's going to be a vertical stretch if that something we multiply is a number bigger than 1. Okay.
So it can't be 1, it has to be.
Well, if you multiply it by 1, is it going to change it? Because yeah, it has to be bigger than 1. So like if we take our X squared idea and I multiply that by 3, it's not going to shift it in any direction. Just multiplying by 3 is going to take that graph and just pull it up and stretch it vertically. It's going to make it look like it got skinnier. The red one is the one with the vertical stretch. It looks like it got skinnier, right? That's what a vertical stretch is going to look like. In that same idea, a vertical compression is A times the function, but that A is between 0 and 1. So that'd be like 1/3, 1/2, 1/8, anything between 0 and 1. Okay, that's going to be a vertical compression. You also might hear it called a vertical shrink. Compression is more the contemporary term for that, and the more official term. So if I go to that, instead of putting 3 in the front, and I put 1/2 X squared. Here's the original in blue. Here comes the 1/2. It spreads it out. So compression, think about that silly putty again. If you pressed it down, it would spread out. You know, when you had that ball of silly putty, if you pressed it down, it spread out to the side, right? That's what's happening with the vertical compression. You multiply by a small fraction, like 1/2, 1/3, 2/3, 3/4, anything smaller than 1, then it's going to be a vertical compression. Okay, that multiplication is happening on the outside. Again, vertical things happen on the outside. Horizontal things happen on the inside.
Okay. On the vertical compression over there, greater or less than 1, and then
but bigger than 0.
bigger than,
so anything, you know, we're not dealing with a negative here at all. The negative does something totally different. Okay, it's like a separate thing. The negative, if there's a negative, it's a separate thing. Maybe that's where you're headed with that. We'll get there. Okay, so any small fraction there, you know, 28 over 29 is a small fraction. It's almost 1, but it's still small compared to, you know, not an improper fraction like 3 over 2. That's bigger than 1, so that would be a vertical stretch. So you got to keep in mind that sort of thing. All right, let's look at horizontal stretch and compression. Okay. Horizontal stretch. Y equals F, and then the A that you're multiplying by is on the inside, and it's between 0 and 1. It's the opposite. Opposite things happen with horizontal things. All right. So if we look at our same idea here, parentheses, and let's say I did a small fraction, 1/2 X, and then square that on the outside. Horizontal stretch is like taking the silly putty and pulling it this way, right? That's going to make it wider. A horizontal stretch and a vertical compression are hard to tell apart on a graph. The equation, it's easy to tell them apart because the vertical thing is going to be on the outside horizontal is going to be on the inside. They're hard to see on the graph, but we can see here that that's obviously stretching it out side to side. So we know there's either been a horizontal stretch or a vertical compression happen to that. And without a little more detailed inspection of that graph, you wouldn't be able to tell which one, because there are vertical stretches or vertical compressions and horizontal stretches that are the same, but the equation looks much different. So those things happen out of that. So inside small fraction is going to be a horizontal stretch. Inside large number is a horizontal compression. Horizontal compression, y equals f of a times x, where a is bigger than 1. Again, just a view of that with the x squared function. If I do a 3 in there with the x and then square that, much in the same way as the vertical stretch does, it makes it look skinnier. So a horizontal compression by a factor of 3 is the same as a vertical stretch by a factor of 9 on the x squared function. But they look identical on the graph. The equation looks much different though out of that. So big number on the inside, we're looking at horizontal compression. Small number on the inside, we're looking at horizontal stretch. It's the opposite on the vertical. If it's on the outside, big numbers of stretch, small numbers of compression. All right. Here's where the negatives come in. Reflection across the x-axis. That's just going to be a negative on the outside. It's like a -1 on the outside. Okay. If I do that with my graph here of the x squared function, a negative out in front and then x squared. You see the blue one is the original. Here comes, flip it across the x-axis. Right there, the red one. That reflects it across the x-axis. Again, outside does things vertically. Reflecting across the x-axis is a vertical movement, even though it says x-axis. Okay. Reflection across the y-axis, a little tougher to see on the x squared function because it's a negative on the inside, and with the x squared function, it's symmetric anyway. So when you flip it across the y-axis, it looks exactly the same as it started with, but it really is it spins it out of that. So might be easier to see if I swap to the x cubed. So if I clear that and go x to the third as the original, and then do parentheses negative x. Let's do that. Parentheses negative x raised to the third. So the blue one is going to be the original graph. And then here comes the reflected across the y. You can see it spun there. The x squared one, you're not going to see any difference. It's going to land right on top of it because it's symmetric across the y-axis. But here we can see that spinning it across that. All right. And then if I do negative and then x cubed, just so you see that reflection across, it looks almost the same as it is exactly the same if there's nothing else in the equation as the x-axis reflection, just because that's the way the exponents work there. So, but anyway, but as you have more work to do, we're going to look at some specific problems and say, hey, what's going on with this? What would be the equation if we shifted it down 5 units or something like that? So that's what we're going to look at. So let's look at that. here's our original function. F of x is equal to x squared. And we want to write the equation for each translation or transformation. The difference in those is a translation is moving it this way or that way or up or down. A transformation is the stretches and the compressions. That's not that you have to know that difference, but that's why they use both words there. Let me see that. All right, so if we wanted to write the equation for when this function is shifted down 5 units, if we're shifting down, that's going to be a vertical shift, right? The vertical shifts involve addition or subtraction. So if we're going down, are we going to add 5 or subtract 5? Subtract 5. So it would be y equals x squared minus 5, which shift it down 5 units. Back to the original, and it's like a separate problem. Shifting that original f of x equals x squared, we're going to shift it left 2 units. So left is a horizontal shift. So horizontal shifts happen on the inside. So I know I got to have some parentheses. The squared on the outside. X plus 2 on the inside. Good job. X plus 2 on the inside. If we're going left, it's a plus. If we're going right, it's a minus. Let's make it more fun. Let's shift it up 6 and right 7. So 2 things. So what have I got going on here? I'm going to need a parentheses because I got some horizontal stuff happening. Is it plus 7 or minus 7?
Minus 7.
Minus 7 because we're moving to the right. And then plus 6 on the outside because we're moving up. Okay. Horizontal happens on the inside. Vertical happens on the outside. Keep that in mind. Let's do a vertical stretch. And then down 3.
Times x, or 4 parentheses x.
Do I need parentheses here? No, I'm not doing anything horizontal, right? So I'm only doing a vertical stretch, and then I'm shifting vertically down 3. So I'm not going to need any parentheses. Minus 3 there, yeah. 4x squared minus 3. Same thing, just beating this dead horse here. Horizontal compression by a factor of 4. That's it. Okay, so I'm gonna have to have parentheses because I'm doing something horizontally. What goes in there with that? So if we're doing a horizontal compression, we know that the number inside has to be greater than 1, so the factor is 4, so it's going to be 4x inside, and then that's it. One more. We'll move on to something else. Let's say we have a reflection across the x-axis and up 10.
Going to be any number for the reflection?
Well, it didn't say anything about a stretch or compression, so what number does it have to be? 1, yeah, -1. Yeah. -1 x squared. That negative takes care of our reflection. There's not inside of parentheses, so that's how we know. And then plus 10. That's right. That's our up 10. Okay, so reflection across the x-axis is the negative that's out in front, and then the plus 10 is our up 10. If it were reflection across the y-axis, the difference would be just that. If it said reflection across the y-axis, put that in parentheses because that's the horizontal move. Okay. Not too crazy there. It's easy enough. All right. Let's look at this kind of problem. These are a little bit more difficult for some folks, but some folks seem to catch them really easy. So the point 2, 6 is on f of x. So that means we've got some function, and 2, 6 is on that function's graph. That's an ordered pair that's in there. Okay. And what would 2, 6 be on y equals -3 f of x minus 1? Yeah. So we got to think what transformation or translation is happening on our function. What does this tell us? What does the -1 tell us? It's horizontal. How much? In which direction? Right. Right 1. Yeah, because it's a minus. So we're going right 1. What does the -3 out in the front? Reflect where? Reflect x-axis. And then what? It's the 3 part, dude. The negative is the reflection. The 3, excuse me, vertical stretch. Good job. These are the ones that really tell you, do you understand the theory in translations and transformations, okay? So if it's going to reflect across the x-axis, that's going to change the y value. And a vertical stretch is going to change the y value, okay? The right 1 is going to change which value? The x, okay? So if we move 2, the x value of 2, right 1, where would we be? At 3. If we reflect 6 across the x-axis, that would move it down here. That's a vertical movement. So what new y value then would be -6, and then we're stretching it by a factor of 3. -3 times, or 3 times -6 should be -18. Okay, that's a little, obviously a little tougher than what we were doing. But the idea is figure out what transformation is happening. Moving it to the right one, we know that left and right stuff, horizontal things, affect the x value in whatever way that it says. Okay, things on the outside are going to be vertical things. If it's a negative on the outside, you know it's going to be a reflection. It's going to change the sign of the y, and if it's a number out there, it's going to multiply times that new y out of that. So same point, and let's do another scenario. What would that 0.26 turn into on y equals f of x plus 4 and then minus 8? So what does this tell us to do? Left 4, and the minus 8 tells us down 8. All right. So if I move to the left 4 from 2,6, what's left 4 units from 2? Yeah, negative 2, because I go 4 units that way, it's going to be negative 2. And then 8 units down from 6. Also negative 2. This is the y value this time. And we've followed that transformation for that particular ordered pair. The key, though, is getting that transformation written out first. It makes it much easier. Some people can just see it and do it without having to worry about that. They just know. I just what's happening. But not necessarily always the case. Yes, ma'am.
So the x plus 4, the plus 4 makes it go left.
Yes.
So basically, when it's x plus 4, pretend it's a minus 4 because it's subtracting 4 from.
If it's a plus sign in there, go left. If it's a minus sign in there, go right. That, ever how you remember that. It's always confusing if you say change it to a minus, because then people will actually change it to a minus, and that doesn't work. Because then you'll think, oh, it's a minus sign now, so it's going to the right. And so I don't ever change it. I just think, okay, if it's a plus sign in there, I'm going left. If it's a minus sign in there, I'm going right. When it's on the inside. All right, let's look at another scenario that could come up. We want to describe. This one's a little easier. The transformation. Spell transformation. All right. For f of x equals square root of x. So just changing which function we're using here. Doesn't necessarily matter what function I'm using. Instead of x squared, I'm using square root of x. Okay. Our first transformation that they're giving us the equation for is that y is equal to the square root of x plus 3, and then on the outside minus 6. What does that tell us is going on? So we're going plus 3 tells us go left 3. The minus 6 tells us go down 6. Left 3, down 6. Describing that transformation. Negative 3, square root, x minus 5. That's it. All right, I heard right 5. I heard reflect across the x-axis. Reflect. Across x-axis. And then what else? Vertical stretch. How do we know it's a stretch and not a compression? My factor of 3 is a larger number. It's not between 0 and 1. Okay. Vertical stretch. And you might say by a factor of 3. That's probably the most descriptive that you're going to get out of that. Okay. One more, and then we'll be to the last section of the day. Square root negative x plus 7, and then minus 16 on the outside. Good. That negative x there, that gives us a reflection across the y-axis. Left 7, down 16. Good job. Easy stuff, right? Much easier than the moving the ordered pair. But still, things you got to do. All right. Function stuff. That ends up chapter 3, and we're going to start chapter 4 today. Remember, your first test contains chapter 3 and 4. The rest of them will be one single chapter per test. So we'll start chapter 4 today and get going with it. Chapter 4 starts out not too bad. It talks about linear functions first. So we got some general knowledge about functions. We've been working with functions and their domains, ranges, intercepts, all that stuff. So in chapter 4, what they end up start doing is talking about different kinds of functions. So the first section is about linear functions, and then we get into quadratic functions and various other kinds in that chapter. So linear functions, basic form, f of x equals mx plus b. If you're going through school right now, that form, you start learning that, I think, in 7th grade at the latest. Some 6th grades are teaching that stuff, but our 7th graders at my school are working with that, I know. 6th grade's in another building, so I don't get to see what they do. So m being the slope, b is your y-intercept. Okay, so very simple stuff there. Functions have things called function value. Talk about that some. Function value. So let's do an example of that. Find the function value if f of x is equal to 3x minus 7. That's in that linear equation form. Slope of 3, y-intercept of negative 7. They want us to find f of negative 2. Okay. What does that tell us to do? Plug in negative 2 for x. Just work that out. Be negative 6 minus 7, negative 13. So f of negative 2 is equal to negative 13. That is also the same thing as the ordered pair, negative 2, negative 13. Those are the same thing. Okay? Bouncing back and forth between those is nice to be able to do. Yes, sir.
So is it only called slope if you're talking about linear function?
Linear functions are the only ones that have slope. There are slopes that occur like an average rate of change. It's usually called an average rate of change if it's something that's not a linear equation. That's usually what the difference in the, even though they're both slope, but average rate of change is usually what you call it on something that's not linear. Good question. Good question. All right, so function notation, ordered pair notation, they're the same thing. Know that they are the same. Know how to bounce back and forth, because a lot of times they'll give you some information about a function and they'll put it in function notation, and sometimes that just blows people's minds. But if I give them the exact same problem in ordered pair notation, they can do it without batting an eye at it. It's not a problem. So know that that's the same thing. And that if this bothers you, write it like this and then do the work. Okay? So if something's not the way you want it, change it. Good. If you can. Change the things you can change. Learn to deal with the things you can't. All right. Here's a function. G of x equals 2/3 x plus 5. And they want us to find the intercepts. Oh, me, what does that mean? What kind of intercepts could they be referring to? X and Y intercepts, okay? So if you're going to find an X intercept or a Y intercept for this, you got to know how to do that. One way would be graph it, and then you're going to have to guess if it doesn't cross at a nice place. But the good thing is we know some algebra, and if we want to find an X intercept, where do we put the 0? In the Y place. So we set the equation equal to 0. Solve that thing. Good old math. Divide by 2/3. I'm going to do the kind of cocky thing of multiplying by the reciprocal. Make it sound awesome. It's really not that any different. It's the same thing. The difference is you got to be careful if you're going to do that with the calculator. If you divide by a fraction, you got to put that fraction in parentheses. Like if I'm going to say -5 divided by 2/3, I got to put 2/3 in parentheses. If I don't, it don't give me the right answer. It gives me that as a decimal. If I want that to change back to a fraction using my graphing calculator, hit math, enter, and it changes back to a fraction. Not that I couldn't do that without a calculator, but it is good to know. So your x-intercept is the ordered pair, -15/2, 0. Okay. To find a y-intercept, where does the 0 go? In x. So we're actually just finding the function value, g of 0. 2/3 times 0 plus 5. And then 2/3 times 0, 0 plus 5 is 5. So g of 0 is 5. The ordered pair, 0, 5. Here are your intercepts. X-intercepts, y-intercepts. You can use your graphing calculator to graph that if you need to. It can be helpful. Example C, h of x equals 8. What do we know about that equation? It's just real talk here. It's a horizontal line. Where at? At 8. So if it's a horizontal line, what's the slope? 0. Good job. Does it have an x-intercept? No, none. Okay. Does it have a y-intercept? Not just 8, but 0, 8. Yeah, that ordered pair. I'm kind of being picky there. That's an ordered pair. So know that kind of thing. Very, very important. Linear function. Got to know that kind of stuff too. Those are the oddball ones, the curveball things out of that. All right. Let's talk about the average rate of change and writing a linear model for a particular set of data that we're maybe given. Okay. So a whole new page here. Average rate of change. We've already kind of discussed that. An average rate of change is just slope. And we know that the slope, usually represented by m, has a formula y2 minus y1 over x2 minus x1. Okay. All right. Now, from there, what we can look at is if we're given a set of data and they ask us to write a linear model for the given data, we can write an equation for that. So I want to show you some stuff with that. Write a linear model for the data. Okay. And it's going to be at x and y. We use order pairs 20, 50, 30, 47.5, 40, 45, 50, 42.5, and then 60, 40, And we'll go one more. We'll do 70, 37, 25. Okay. Now, as we progress through the course, you're going to be given more and more function types to write models of. Here, they tell us to write a linear model. So we don't really have to test whether or not this data is linear or not. Okay. As we progress through, when we start getting different kinds, they'll say write the best fitting model for this. And it may not be linear. It may be quadratic. It may be cubic or something weird like that. Could be exponential, you know, depending on what's going on. So we really don't have to test that for this. They told us do a linear model. And the way you want to do a linear model is you just need to pick two ordered pairs to find the slope between. I want to pick easy numbers, right? So I'm thinking if I pick this ordered pair and this ordered pair, the math's pretty easy on that, right? Because they all end with zeros. So my math's not so hard there. Okay, if I pick those two ordered pairs and I try to find that slope using that slope formula, I'm going to plug that stuff in. So 50 minus 40, I'll just do it in that order. And then that means I got to go 20 minus 60 on the bottom. 10 on top, 20 minus 60, negative 40 on the bottom. That reduces to be negative 1/4 as the slope. So that gives me part of my equation, y equals negative 1/4 x plus b. I need to find out what b is. I need to find that y-intercept. How can I do that? But, well, I can't just replace x with 0 because I don't know what the y value is when x is 0. But I do know what the y value is when x is 20. So I could plug in one of those ordered pairs. I'm going to use one of the ones that I use to find my slope. So I'm just going to pick 20, 50 and plug in 50 for y and 20 for x. What's 1/4 of 20? Negative 5, right? Negative 5. Negative 1/4 of 20 is negative 5. And then I got 50 over there. How do I get b by itself? Add 5. Real simple math here. 55 equals b. My linear function that I've built, the linear model, is f of x equals negative 1/4 x plus 55. That doesn't necessarily mean that for every one of those x values, if I plug it in to this equation, I will get exactly, you know, if I plug 70 in, I may not get exactly 37.5. I've just found a linear model that fits those two ordered pairs. The other ones should be close to it because they told me it was going to be a linear relationship there. Okay, so I've just found an equation of that. I'm not necessarily finding the best fitting equation. I'm just finding an equation.
With those ordered pairs, would the slope be constant throughout all numbers?
Not necessarily. It could be. With this set, it actually is, but that's not always the case.
I don't know if that's how most of these would be.
In this section, yes, probably will be. But as we progress later on, it won't be quite as often. They'll be a little bit different each time, but they will all be kind of close. Out of that. And then we'll learn a trick on the calculator how to deal with it when it does that. So it's not as daunting a problem. All right, so finding a linear model, finding an equation of a line. Doing just that. Nothing really more difficult than that. Let's look at this. Let's say we're given two functions, two linear functions. Let's say f of x is equal to 3x plus 5, and g of x is equal to negative 1/3 x plus 1. Okay. Two functions that are linear, and we want to answer some questions about those. Okay. The first question will be find where f of x equals g of x. What in the world? where does f of x equal g of x? What does that even mean?
Where they intersect each other.
Exactly. Where they intersect each other. Where they're what are they running into? Where are they hitting each other? We know they're going to run into each other because they don't have the same slope. You know, remember some general knowledge about linear equations. If they have the same slope, then they're parallel. They'll never intersect. We know these two are going to because they have different slopes. How can we find that algebraically, like with math and not graphs?
Be really good at that.
Well, yeah, but what does this say?
You can set them both.
It says they're equal to each other, so just set them equal to each other. So I'm going to set 3x plus 5 equal to negative 1/3 x plus 1. And then that's an equation that only has one variable in it, x. And that's solvable for us. So we're going to get x by itself. So I would add 1/3 x to 3x. And I'm going to do two steps at once. I'm going to subtract 5 from 1. Red make purple, so I'll make a purple step here. Negative 4. And then 3 plus 1/3 is 3 1/3. So it'd be 3 times 3 is 9 plus 1 is 10 over 3 x. You can use a calculator to do that. It doesn't bother me. I wouldn't, don't convert to decimals. This is my fair warning there. Because that's a repeating decimal and you never can type enough 3's in there for it to work out right. Okay. So always convert back to fractions on the calculator. That's math, enter. Make sure you remember that if you use calculator help you.
Question on that: if something happens by accident and you put the decimal in where the slope is, if you're trying to graph it, will it still graph?
It will. If it's a terminating decimal, it'll graph it correctly. If it were like 1/3 as a slope and you typed in 0.33, it's not going to be exactly the same. It'll be just a little bit off, but it will still graph it. It won't. It'll just graph it using whatever you typed in. All right. I'll show you a calculator in just a minute. Yeah, I'll show you a calculator with the calculator in just a minute. Another option for that. So here, what's the last thing we do? Divide by 10 over 3. I don't do that, so I'm going to multiply by the reciprocal. And those cancel out. There's x by itself. And then we get negative 4 times 3, negative 12 over 10, which will reduce negative 6 over 5. That's the x value. How in the world do I find a y value that goes with that? Plug it in. Good job. So it does it matter which function I plug it into? No, just pick one. Pick one you think is going to be the best. Heck, all right, let's go to the first one. F of negative 6 over 5. 3 times negative 6 over 5 plus 5. Gotta love working with fractions because it's fun. Negative 18 over 5 plus 5. You can do that with a calculator if you want to. You don't have to. Just a little general knowledge of that's 25 over 5, and then subtract those two. 25 minus 18 would be 7. 5. Right. So f of negative 6 over 5. So where are they intersecting at negative 6 over 5? 7 over 5. That's doing it algebraically, which is maybe the best way to do it because you get an exact solution of where they're crossing. Okay. With the graphing calculator, you also get an option of graphing it and see where they intersect. So with that, I'm going to hit the y equals button on my calculator. I'm going to clear out all this other junk that I've been doing. Okay. So I'm at y equals, and in y1, I'm just going to type in f of x, 3x plus 5. And in y2, I'm going to type in negative 1/3 x plus 1. Then we'll hit graph. We can see they're intersecting there, right? Your calculator actually has a function that'll find that intersection. If you hit second trace, it gets this calculate menu, and much the same as we were finding maximums and minimums. You've got number 5 choice of an intersection. So number 5, and the first curve You know, it's saying this one here. I'm gonna move to the left of that. Hit enter. And then second curve to the right of that. Enter. And it asked me to guess, and I'm actually going to try to get close to where they're intersecting. And that's pretty close. I'm just kind of eyeballing it there. And then hit enter. Negative 1.2, positive 1.4. Well, negative 6/5 is negative 1.2. And then 7/5 is positive 1.4. Now, here's where that kind of falls apart. If it doesn't cross at a really nice place that is a terminating decimal, then you're going to have to make some sort of estimate here. But this gets you an idea of how you could do it graphically. And it does show that intersection, which is the first way that you guys told me that you could find out where they're equal to each other at. Okay. Now, you could also be asked the same two functions. I'll bring them back down here and copy and paste action so I don't have to scroll back and forth. For those same two functions, you might be asked where is f of x greater than g of x. How can you do that? Yeah, same way we did the equation mathematically. You're going to set f of x, 3x plus 5 greater than g of x, negative 1/3 x plus 1. Do all of the steps the same. Minus 5 plus 1/3. That'd be 10/3. X is greater than negative 4. Multiply by the reciprocal again. Three over 10. Sorry, blank it out there. And then x is greater than, we know that simplifies to be negative 6/5. The difference is this is the end. You don't have to find the y values that go with that. We're just looking for where is that happening at, where x is greater than negative 6/5. That's where f is greater than g. We put that in set notation, or interval notation would be from negative 6/5 to infinity. Those would be the where. If it asks for where is f less than g, set that up. Flip the inequality symbol around. If it asks for where is g greater than x, turn it around and set the problem up the way they're doing that there. Graphically, that's a little more difficult to do. You got to keep in mind which one's which. The blue one is f of x. The red one is g of x. So where is f of x greater than g of x? It'd be in this part. And you're looking for the x values for that. So that's, again, unless it works out to be nice terminating decimals like this, you're going to have to make some sort of estimate at some point for that and go from there. All right. So basic linear function things. Nothing really just crazy about this section that you have to do. Some practice problems that you might want to look at in your textbook, 252, 11 through 51, exclude 47. That's we don't cover in this course. 264, 7 through 65, I believe is right. And then 41, page 287. And before you guys get out of here, I don't take attendance for a grade, but I do want a record of it for my purposes, because it's always come up. Hey, was so and so in your class such and such day for whatever reason, and so I would like to know if you're here or not. So let me get a sign-in sheet here, and I just write your name legibly on this piece of paper before you leave, and so that I can know that you're here. Canvas quiz. That chart will also be posted on Canvas. Canvas quiz is already out there actually for you to be able to do. And if you got questions, email. I'm glad to help. And if you got to, we can set up a Skype session or whatever, something, make it work. Okay. Maybe. I don't know.